On Tuesday, we did derivatives of vector functions. And now we're going to do integrals of vector functions, and that's all we're going to do with them. So what we're going to be talking about with integrals is going to be distance and displacement. All right, so that's really the only two applications that there are. So basically, it's like these two formulas. So vector displacement over an interval a, b. So this is a time interval. T is going from a to b. All right, the displacement is the integral from a to b of the vector function. So I just do the integral of the vector function. The velocity. So where v is the velocity. So maybe I should put that in here for v equals velocity of our given vector function s of t. All right. So then the displacement is the integral of the velocity function, and then the distance from a to b is the integral of the magnitude of the velocity function. So that's just like when we did distance and displacement back in the day when we first did integrals. We did distance and displacement of real valued functions. All right, so all our functions at that time were real numbers. Vectors are not real numbers. Their components are real numbers. They're made up of real numbers, but vectors are not in fact real numbers. They're not numbers at all. They're vectors. So they have a whole different, you can study what fields are. They're their own field. All right, so yeah, so it's similar to what we did with real valued functions where the displacement was the integral of the velocity and distance was integral of speed. It's the exact same thing, except now they're vectors instead of real valued functions. All right, so let's look at our old friend. I like to just take the same familiar shape and just do a million things with it. So now think of all the things we've done to this shape. So we've created this shape, we found the tangent line to the shape, then we just learned to find the length of the shape, and then we learned to find velocity and acceleration on the shape, and now we're going to learn to find displacement and total distance traveled on this same shape. But then all of it generalizes to any shape at all. All right, so if we have s of t equals sine of 2t, this is what this is, sine of 2t cosine t. All right, and let's say I want to find displacement and total distance traveled, and especially in a vector context, they won't necessarily say total because it's like you have a distance from here to here. There's no net distance. I mean, the displacement, I don't know. Sure, why not? It's total distance. You can say that if you want. Anyway, find a displacement and total distance over the interval t from 0 to pi. All right, so that's what we're going to do. All right, so let's start with displacement. So displacement is going to be the integral from 0 to pi of our velocity function. Oh, I didn't find the velocity function, did I? All right, well, let's do that next. Let's find the velocity function. I'm just going to change colors so it'll fit in here nicely. So what is it? 2 cosine 2t. I mean, I could copy it from before, but I don't feel like going to look for it. Negative sine of t. There you go. That's the velocity function. Okay, so now I can use that in here. And so I can say my displacement is the integral from 0 to pi of the vector 2 cosine of 2t negative sine of t dt. All right, so what does that mean? How do I do the integral of a vector? Well, just like derivatives, you just do it component by component. So I'm actually going to write it that way. You don't necessarily have to, but I'm going to say what this integral really means is the vector whose components are the integral from 0 to pi of 2 cosine of 2t dt and the integral from 0 to pi of negative sine of t dt. So you could just do this integral directly from here to what I'm going to do here, but I'm just sort of showing that we should have a sense of what the integral of a vector means. It means the vector whose components are the integral of each component. All right, so I mean that's sort of common sense anyway. So this equals, so I just do my antiderivative. I'm going to do antiderivative cosine is sine of 2t, keeping the inside the same 2t, and then I have to do 1 over g prime, which is going to be 1/2, which is going to cancel the 2 right there. all right, which really just brings you back to sine of 2t. So you can think about that or work it out separately if you want, but the antiderivative of 2 cosine 2t is sine of 2t. All right, and then the antiderivative of sine is cosine t from 0 to pi. You know, doesn't it seem like we started out with sine of 2t and cosine of 2t? I ended up with sine of 2t, cosine of 2t. So kind of because we did the derivative and then we did the integral. Oh, it's worth thinking about. Anyway, this equals, let's see, sine of 2 pi is 0, sine of 2 times 0 is 0, cosine of pi is negative 1, cosine of 0 is 1. Oh, I forgot to put the minus sign. Is 1. All right. So that's just doing this integral and this integral. So I get 0, negative 2. The displacement is 0, negative 2. So from over the time interval 0 to pi, the displacement is 0 to negative 2. And I'm going to show you on the graph what that means. So that means that from time t equals 0, which is here, to time, all right, let's put t equals 0 there, to time t equals pi, which we discussed earlier, t equals pi is down here, because it takes 2 pi to draw the whole thing. So just going to here is pi, okay? If I go from time 0 to time pi, what is my physical displacement from that point? It's 0, negative 2, right? Because I went down 2. This is 1, this is negative 1. So it went down 2. This is my displacement, 0, negative 2. That's my displacement in time from 0 to pi. All right, so that's how we do displacement. So this is displacement. So next we will do total distance.